All right, according to our measurements, what do we get for the longer sides? Go ahead.
I have 70 millimeters.
All right, so just about 70 millimeters for both of these. And the shorter side? 35-ish. All right, and now, what about the angles? What do we get for angles? So 75 degrees here, 75 degrees here, and what do we get? Somewhere about 30 degrees, right there. Okay, so what we're looking for now is eventually we're going to see if there is some sort of a relationship between congruence and between angle congruence and side congruence. So first, let's do some labeling here. An isosceles triangle that the congruent sides are called my leg. Each one of them is called the leg. And the non-leg is called a base. The non-leg is called a base. Base does not mean bottom, although it can. Oftentimes, we are familiar with the triangle being drawn like this, right? We almost always put that one on the bottom here. And there's no rule that says it has to be that. It can be oriented any way. So don't think of base as bottom. Think of base as not legs. Okay. Well, it turns out that since I'm calling this my base, that these angles right here have a special name. That this angle and this angle are called my base angles. I know, shocking. They're attached to the base. They're called base angles. Which leaves me with one more thing. We have base, legs. So what do you think up here might be called? Oh, so tempting. Go ahead.
The leg angle.
You'd think it's called leg angle, but it's not. They're screwing you up. It's called the vertex angle. I know. Don't know why. Because all of the vertices are vertexes. So why do we call that one? Well, it's the not bases. So let's go on. Now that we have labeled all these, we have base angles, we have legs, and we also have a hint as to what might be true. What is true about base angles? What's true about the two angles? They are congruent, which brings us, right now it's a conjecture because we haven't proved it, but it brings us to the wonderful world of base angles theorem. Base angles theorem says this. It says that in an isosceles triangle, make sure to spell isosceles correct. You can abbreviate triangle as so. Isosceles. Iso means same, and sceles, I think actually means like measures or sides, but unclear on that. So in an isosceles triangle, base angles are congruent. Notice it doesn't say how big they are. It just says if one of them is 20, the other one's 20. And it only applies to an isosceles triangle. So in a diagram, it might look like this, where we have an isosceles triangle. We know it's isosceles because it's going to be labeled as such. So we've got a triangle there. Since the sides are congruent, we also are going to know that I have congruent angles. I have congruent angles. So we can also label a few things here. If I called this A, B, and C. So if AB is equal to AC, in other words, those two sides have the same measure, then angle A is congruent to angle C. So we've got one set of congruence travels on to another set of congruence. So it turns out that the converse, that is, when I flip the ideas here, instead of starting with isosceles, I'm going to start with the base angles congruent. Now, I actually can't call it base angles yet because I don't know it's a base angle. So how would we actually start it? We'd start it like this. If two angles in a triangle are congruent, then the sides opposite are also congruent. So what would the diagram look like this? It actually turns out that the diagram's exactly the same. So I'm not going to redraw it. I'm just going to switch around the content here. So I'm actually going to say this. If we have two angles congruent, measure of angle A and the measure of angle C, congruent, excuse me. Since they're congruent, I should get rid of the M right there. There we go. If two angles are congruent, then I have two sides that are equal, or you could say the side lengths are equal, or the sides are congruent. So let's use and apply this in this context. Clearly we have an isosceles triangle because of the two congruent marks here and here. So because of that, this angle is congruent to this angle. So I can actually set up to solve for x if I wanted to. So it looks like this. I know that 3x minus 11 is equal to 2x plus 11. The reason for that is the base angles theorem. The base angles theorem. Now we're going to use our wonderful skills of algebra. So I'm going to add 11 to both sides. Here, while I'm at it, I'm going to subtract 2x from both sides, do it all in one step. And over here I'm left with x. And then on the other side I'm left with 22. Left with 22. So that gives me one of the variables. So now what we can do is we can take this 22 and substitute it into either one up here or here. And when we do that, we get 55 and 55. So what we see is, since this is a triangle, the triangle sum theorem says 55 plus 55 plus 2y equals 180. And when we solve that, we get all the way to 35. So y ends up being 35. Now let's take a gander at one last problem here. Because we have congruent sides right here, we also therefore have congruent angles in these two places. So this has to be x minus 2 degrees. Now what we can do is use the triangle sum theorem to set up, say, all three equal angles sum to 180. And in doing that, we can find out the value of x. So 6x plus 6 equals 180. And I'll do two steps in one to get x is 29. Now I can take the 29, place it right there to get 27 degrees. And now I can finish up to find out what y is. So 3y plus 27, because of linear, sum to 180. So 3y equals 153. So therefore, y is 51 there. And we've got x's and y's all there. Now you can turn the page over and work on the other side.